Good morning, good afternoon, good evening, wherever you are located in the world. And thank you for joining us for this month, March's webinar for AMETEK solid-state controls. This month, we are touching on frequently asked questions, and that is from all the surveys that we've sent out over the last few months. So hopefully you'll get some good information from here. Once again, as always, please type in the chat bar and let me know that you can hear me okay. That would be appreciated, and it will also give us a chance to let everybody else get into the room. Okay, thank you, Taylor, for letting me know you can hear me. I didn't want to go any further until somebody said they can. Don't want to talk to myself all day. So just go through some introductions. My name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls. I'm based in the Stafford office here south of Houston, and our head office is in Columbus, Ohio. I have 20 years in the industrial UPS industry. Oh, goodness me, that makes me feel old. And I've worked with all major UPS and charger manufacturers. I joined AMETEK Solid-State Controls about 5 years ago. So I've been with AMETEK for quite a while now. There's going to be a lag of around 30 seconds between you hearing my voice and when I see a question. Basically, Webinar Jam has to convert this webinar into packages that iOS devices, Android devices, and Windows devices can display. And there is some processing time that it takes to do that. So it's about 15 to 30 seconds between when I speak and actually when you hear it. So therefore, if you type in a question or a comment, I'm not going to see it until a little bit later after I've spoken. And what I tend to do because of that, and because I do assign some time at the end of the webinar, I tend not to look at the questions that people are asking as I go through the webinar until we get to the end of the webinar. Okay. So please, if you do post a question, you're quite welcome to post a question at any time. I will go through them at the end. Webinar Jam is the platform we use, and it does have a panic button. And what that means is if we have any internet connection issues, if I see a lot of comments coming in saying lost connection, then what I can do is I can press the panic button, and Webinar Jam will automatically create a new room and invite everybody into that room, and we will carry on from where we left off seamlessly. Another popular question is, will the webinar be recorded? And the answer to that is yes. As somebody who is registered for the webinar, you will receive a link of the recording from Webinar Jam after the recording is completed. That is in the Webinar Jam format, so you do have to watch that from start to finish. You can't fast forward or rewind that webinar. So what our fantastic marketing department do is they download that and convert it into an MP4, and then they upload it back into the AMETEK SCI YouTube channel, and therefore you can watch it to your heart's content, pause, rewind, and do whatever you would like to do and fit it into your day. The webinar should last around about 1 hour. I'm really trying to make it last an hour. The last one was about an hour and a half. So I'm doing my best to make it only last an hour, because I understand your time is precious and you don't have that much time to give to this in the day. And that last bullet item, that there was going to be 2 special guests, that is me copying and pasting from a previous webinar. That is not going to be the case in this, and I should have picked that up before I published this. That's my fault. It's only going to be me on the webinar today, so I do apologize. So as I discussed, we're going to go over some questions from previous webinars and surveys. And the first question that we're going to go over today, somebody commented, was, please explain grounding on your UPS and mention high resistance ground networks. Very, very good question. It's something that comes up quite frequently in our day-to-day work. So the first thing that you have to understand is that the UPS is a separately derived system. And the explanation for that is premises wiring systems whose power is derived from a battery, solar voltaic systems, or from a generator, transformer, or converter windings that has no direct electrical connection, including a solidly connected ground circuit conductor, to supply conductors originating in another system. That's the official term for it. The easy way to look at it is it's a separate system where the ground connection can be completely separate to the original grounding in the building. Hopefully, as we go through these slides, it will become more apparent. So the simplest separately derived system is an isolation transformer, a transformer where the primary winding and the secondary winding have no electrical connection to each other. None of the wires physically touch each other, okay? And as you can see here on the primary winding, that will be the neutral will be connected to ground as part of the distribution system, either the MCC, or if it was in your home, it would be your breaker panel outside your house. Okay, but what's important to understand is the secondary side, as drawn here, has no ground connection. So that's where the term separately derived system comes from, that the secondary in this case of the transformer, has no connection at all to the building electrical work, okay? And what that means is, in this drawing here, if to comply with electrical code, what you would then have to do is then connect an additional ground. Now you can connect that ground directly to this ground over here and do that. But if you want to comply on a separately derived system, you have to connect the neutral on the secondary side of that transformer to ground to maintain that connection. And separately derived systems are grounded to limit the voltage imposed by line surges or unintentional contact with higher voltage lines, and to also stabilize the voltage to ground or earth during normal operation. And in addition, it ensures a low impedance ground return path that helps or aids the overcurrent protective devices to activate very, very quickly. It gives a nice easy path for any fault current to get back to the overcurrent protective device, whether that's a breaker or whatever it is in your MCC. So the reason why an AMETEK SCI UPS is considered a separately derived source is, as you can see here, there is an input transformer, and it is a isolation transformer. You can see there is no electrical connection on the primary side with respect to the secondary side. And you'll also notice that on our UPS systems, we do not run a neutral to the input to the battery charger. We usually take a 3-phase 480 delta supply from an MCC. And there's absolutely no need. In fact, we don't have anywhere to land a neutral inside our cabinets. So there is no neutral run into the input, the charger input to our UPSs. But you also notice on the output of our system, this is the inverter. The inverter has an isolation transformer, which once again has isolation between the primary and the secondary. Okay, so you can now see from this drawing that these are connected back to your MCC. There is no electrical connection between this output here, the live and the neutral, with respect to the MCC 480 volt feed into the UPS. Okay, we have to actually create a grounding system for you to comply with electrical code. And you can see that we have this jumper bar here that's in all of our UPSs, and it tells you what to do. It says remove jumper wire if neutral is grounded at the bypass source. Okay, and I'll explain that in a little more detail. Because what's going to happen is I've drawn this transformer here, but basically this is representing the feed from your MCC to the bypass of the UPS. Okay, now back at your MCC, this is the neutral, and this is the live or the hot. Okay, and back at your MCC, the neutral is going to be connected to ground. Okay, that's just a given. So on the secondary side, so this is the primary and this is the secondary side. On the secondary side, as drawn here, we have no connection inside the UPS between neutral and ground. So in this circumstance, you would leave this jumper in this position. That's not what we recommend, but if this is how you've run your bypass supply to the UPS, you would leave this jumper in place to connect system ground and panel ground to the output neutral of the system. That's what that jumper bar is doing. Okay, but that's not what we recommend. What we always recommend is that this is going to be a transformer that's located relatively close to the UPS in most circumstances. Okay, so what we always recommend that the plant do is they tie the secondary neutral of that bypass transformer to ground within the transformer itself. And there's a good reason for that. It's because a transformer tends not to fail, especially dry type transformers. So the expectation is that this transformer is going to be installed and then it's going to run for years and years and years, 20, 30, 40 years without any issues, if it's a dry type transformer and it's not pushed to the limits or too much current has been pushed through it. A UPS, on the other hand, whether it's a commercial UPS that usually has 8 to 10 years life, or if it's one of our AMETEK SCI industrial UPSs, it has a lifespan of 20 years. So the expectation is this UPS may need to be replaced after 20 years before this transformer will be replaced. And what tying this ground point to the neutral within the bypass transformer does is it allows us to put the system in bypass and still have the neutral connected to ground while we replace the whole UPS. In most cases, we do have to get into our MBSs, to an external MBS, to make it absolutely safe, but that's the intention. So when you do connect the secondary of this transformer to ground within the transformer itself, you then have to go into the UPS and remove the jumper wire. As it says here, remove jumper wire if neutral is grounded at bypass source. Okay, so we're still connecting the system ground to the panel of the UPS, but the neutral bar itself is not connected to that ground. So we're not creating two points where the neutral has been connected to ground, and we'll explain why you don't want to do that. It's a violation to connect neutral to ground at 2 points. Okay, it's called objectional current for improper neutral connection. So what you can see here is the neutral is connected to ground here. And what they're saying is if neutral is connected to ground here, then you are going to get objectional current in the ground conductor, okay? Because what you want to happen is you want to have your neutral connected to ground here, and then if you do have a fault, then the fault current flows through the ground conductor, and that's the only time current should flow through the ground conductor is if there's a fault, and then that will allow the supply, the MCC that supplies this transformer, to trip very, very quickly and prevent this fault from causing a fire. You know, that's what the return ground path is trying to do. It's trying to make sure that a fault is cleared very, very, very quickly. But if you connect your neutral to ground here and your neutral to ground here, in normal operation, depending on the resistance of the neutral conductor to this panel board and the ground conductor to this panel board, some current in normal operation will be allowed to flow back to this neutral, and that's detrimental to the system, and that's a violation of code. So that is why you should never have a neutral connected to ground at 2 points within a system, which is why you have to remove that jumper in the system. Okay. Now we're going to discuss high resistance ground systems. High resistance grounding can be used in power systems supplying critical processes that cannot suddenly stop. So pretty much any petrochemical refinery or chemical plant that requires continuous operation, and stopping that process would cause danger to people, then you don't want something that's going to cause that system to suddenly stop because of a fault somewhere else. So that's why most refineries and petrochemical plants use a high resistance ground system. It also cuts hazard to personnel. The main advantage of a high resistance ground system over an ungrounded method, where the ungrounded method means there are no connections to ground in the system, is the ability to control transient over voltages coming from an arcing ground fault. Okay, and it also allows you, because in most high resistance ground networks you will have a lamp or some kind of detecting circuit that will tell you that there has been an unintentional ground created on that system. So it allows you to find things and go to them and maintain them. So in this drawing here, we're saying this is from the MCC, and we are now talking about this is a high resistance ground circuit. So there is no direct connection to ground, and I'm not going to go too much into how a high resistance ground is installed, but the basic premise is what they do. Let me just draw it here. Back at the main transformer, they actually, I'm not going to draw it the British way. Let's draw it in the American way. There is a resistor connected between usually the start point of the transformer to ground, and that's why it's called a high resistance ground network. Okay. So in theory, this neutral here is not really connected to ground because there's a resistor separating it. So therefore, we know that this point is not connected to ground because that's the secondary of the transformer anyway. Okay. But in this circumstance, what we have to do, and what all high resistance ground systems do to allow a ground connection at the final load destination, is a high resistance ground usually always uses transformers to feed their critical loads, and the secondary of that transformer is what is used to create the ground path. Okay, So in truth, once again, the jumper would be removed here. We do want to connect the panel ground to the system ground, but our neutrals here are floating. They have no reference to ground whatsoever. The ground is connected on the secondary of this transformer. And what tends to happen is the output of this UPS will be a 208 120, usually on a high resistance ground system. And then it will go feed a big transformer, and then that transformer will then feed an AC panel that feeds the critical load circuits. Okay, but this maintains that the main transformer in the MCC or outside the MCC has no direct connection to ground whatsoever. The only connection to ground is through the high resistance ground circuit. Hopefully that explains things. Jeffrey just asked a question: are you able to get a copy of the presentation? Unfortunately, the presentation is proprietary. We do not give out copies of this, but you can watch it to your heart's content on YouTube, and I suppose you can screenshot each page while you're going through it, but we do not send it out via email. So that's high resistance ground circuits. I hope that explained a bit more about where you're supposed to connect the ground circuits on your UPS system. And it's the same for an automatic transfer switch, for an emergency generator, and things like that. Okay. So the next question is, they asked was, can you tell the pros and cons of a ferro-resonant versus pulse width modulated UPS system? Okay. Once again, very good question. We get asked this all the time. And the main difference in the technologies is the inverter bridge and transformer. There are other differences that are cited that are determined by industries or market segments, given whoever the manufacturer of the UPS is, by their design philosophy. But in general, a PWM inverter bridge generates a series of pulses at a high frequency, and it can be 8 kilohertz or greater. And therefore, you need a smaller filter to produce a sine wave. And also the regulation is controlled by electronic circuits. So there is much more processing power going on inside a PWM system. There's a lot more control, there's a lot more switching going on inside the PWM. For a ferro-resonant inverter bridge, it just generates a square wave at the line frequency. In the US, that's 60 hertz. In Europe and elsewhere, it can be 50 hertz. It does require more filtering to produce the desired sine wave. And the regulation is controlled by the transformer. And a lot of people don't kind of get this idea in your head. So for a PWM inverter, for a modern day electronic inverter, all the control is done by control boards, logics, communication, CAN buses, fiber optics. There's a lot of stuff going on to create that high frequency switching for an inverter. And all the voltage controls and current controls are done through control board logic. For a ferro-resonant inverter, it's all of the regulation is done by the transformer. The transformer is a constant voltage transformer. So the inherent properties of the ferro-resonant transformer limit the voltage of the output of that transformer. It is the transformer that does that. There's no controls in the inverter that does that. Basically, the CVT, the constant voltage transformer, it takes an input square wave and it turns that into an output sine wave that can only go between a very tight regulated output. So let's say it's a 120 volt system. The regulation says that for varying inputs to that transformer, the output will remain steady at 120 volts, just through the inherent properties of a transformer, not through any control circuits. So I hope that explains one of the biggest major difference between the two. This is a sales slide I stole off our marketing department. So you can see at the bottom there, AMETEK SCI is the only manufacturer to offer both technologies. So a little bit of sales spiel there at the bottom, but that's not what I'm trying to do. I'm just trying to tell you the difference between the two. Okay. And here's a table that the engineers at AMETEK Solidstate Controls came up with. They give you the criteria on the left-hand side and then Ferroresonant and PWM, and it tells you the differences between the two. So for a Ferroresonant system, they were developed over 80 years ago. So they have a huge amount of history behind them. They've been in the field for 80 years and are very robust. PWM, easy for you to say, was developed over 40 years ago. So it's only half the age of the Ferroresonant technology. It's robust, but it's hasn't been around for anywhere near as long. For a Ferroresonant system, the footprint or the physical size of the UPS is typically larger due to the larger magnetics, the Ferroresonant constant voltage transformer. PWM has a smaller footprint, especially as you get up into the larger kVA sizes and also for three-phase designs. Audible noise is relatively similar for both models. You will know the frequency of the Ferroresonant transformer, the switching frequency is 50 hertz. So it creates a low frequency buzzing noise, and a PWM, because its switching frequency is 8 kilohertz, it's a high pitch noise that you hear. So they're two very distinct noises, but they are in some respects at the same dBA level. Dynamic response to load changes for the Ferroresonant, it's not as good. It can be up to 23% for the first half cycle, but then we say it will recover quickly within 3 cycles. For PWM, it's 10% for the first half cycle and then full recovery within 3 cycles. Available options, they're both identical, extremely customizable. We've discussed the switching frequency and the filtering and the voltage regulation, but we'll go into the voltage regulation a little bit. For the Ferroresonant, it's magnetically done, and it creates a rock solid tight regulation of 2%. For the PWM, it's electronic monitoring, and I think I may be lying. I'd have to take out the data sheet, and I don't have one with me, but I think it's 1%. The PWM definitely has better voltage regulation. Industrial design, the Ferroresonant is extremely rugged and well suited to harsh industrial environments such as coal-fired power plants, geothermal plants, and steel plants. You know, there is very little that goes wrong with a Ferroresonant system. There's not as many control boards, communications, processors, although we use a processor on our new DSC Ferroresonant system. But they're just robust. They work. It's a tried and tested technology and works really, really well. PWMs are also, if they're designed correctly with an input and output transformer, they're still well suited for industrial design, but they can be a little more susceptible to dirty atmospheres and temperature extremes. Okay, so Ferroresonants are much more suited to the industrial environment. Fault clearing capability, the Ferroresonant, the Ferroresonant design of UPS is just excellent at clearing faults. It's what we call a very stiff source and can supply in excess of 500% of the rated output current of the system for a small amount of time to allow you to clear faults on the load circuits if necessary. For a PWM system, it's less robust. Typically, it's 125 to 150% of rated current. Now, don't get overly concerned about that. That doesn't mean that your fault isn't going to be cleared. What the PWM UPS is going to do is it's going to see the fault, it will transfer to bypass. The bypass supply, which is a very stiff source, will clear the fault. And then either through manual interaction, or if you have the auto transfer switch turned to the on position inside your UPS, it will then transfer back to normal operation if the fault has been cleared. So PWM is not as robust, but it still will fulfill the needs of clearing faults by transferring to bypass. And the expected life for a ferro-resonant is 20 to 25 years. For a PWM, it's also 20 plus years. Okay, so they're both similar. So that gives you a good idea of the difference between a ferro-resonant and a PWM. And once again, this is from our sales team, when ultimate reliability and longevity is required, so therefore an example of that is the nuclear industry, where 30 years of expected life is the norm, then ferro-resonant designs are still the preferred technology. Although our DPP is now Nuclear 1E certified, so our PWM technology can now be installed inside of safety-related nuclear applications. Because it's such a tried and trusted technology, the ferro-resonant system is still the norm. But in applications where space is a premium and HVAC packages need to be smaller, the industrial PWM designs are a good alternative. And examples for that are offshore platforms, remote instrument enclosures or RIE buildings, or retrofit projects where the kVA size needs to be bigger, but the equipment must still fit into an existing space. So, for example, for a 30 kVA ferro-resonant, you could probably quite easily replace that with a 50 kVA DPP, but you could not replace it with a 50 kVA ferro-resonant system because it would be physically bigger. Okay. Before I go on to the next question, we have been asked, how long will AMETEK continue to build Ferro UPSs? There is no discussions whatsoever that I know of that we will ever stop building Ferro-resonant systems. We have changed the technology a little bit. We do use the same display board as the DPP system now, but the inverter technology is still a square wave at line frequency and still goes through a CVT ferro-resonant transformer, and is still very, very robust. And as far as I know, we have no plans whatsoever to stop building ferro-resonant UPSs. Okay. So another question that we have been asked recently as part of our previous webinars and surveys is, could you please explain simple battery technology pros and cons? Now, I want to make absolutely clear before we go any further, I am not a battery expert. I know a lot of stuff about batteries, but I'm not a battery expert. So what I'm going to go over for the next few slides is general terms, not going down into really in-depth stuff about the battery technologies, okay? And here's a table that I found on the internet. I'll give you the website. I think it's on the next slide from where I found it. And it tells you the advantages, disadvantages of each of the technologies. Just clear the screen here. So we can see we've got NiCads on the left. We'll forget this one here because basically that's talking about your house batteries, your 9-volt batteries, your AA batteries and stuff like that. But, you know, one of the most important things is the gravimetric energy density. In other words, it's saying the watts that you can get out of the battery per kilogram. So the higher that value is, the more power per size, I suppose, is what I'm trying to say, you can get out of it. So you can see here that for NiCads, it's 45 to 80. For lead acid systems, it's less. They're not as energy dense. And for lithium ion, they're extremely energy dense. You know, we're talking about nearly 3 times the energy density of the other 2 main technologies there. Okay. So that's one of the main differences, is how much power a battery can get compared to its relative size. Cycle life is also important. For an NiCad, you can get 1,500 cycles for the life of the battery. But for a lead acid battery, it's about 200 to 300 cycles for the life of the battery. Now, for a UPS in standby applications, that's usually absolutely fine. You'd be very unusual to see 200 to 300 power failures on a North American UPS. That would be, if it's a 20-year life, that's 10 power failures a year, which would be very unusual. But the data is there to say, if you are doing a lot of, you're expecting a lot of cycle life, then NiCad's the way to go. And you can see that lithium ion, the two different technologies, they give you more cycle life as well. If fast recharge time is important to you, then NiCads are excellent at accepting recharge current. They can be recharged within 1 hour if necessary. Once again, lead acids, not so great, 8 to 16 hours. And for lithium ion, also very, very, very quick. Overcharge tolerance, NiCads, it's not too bad. They are fillable batteries and they usually have a valve. So therefore, if you do overcharge them, what's going to happen is they're going to vent off some of that water inside the battery. The actual overcharging of the battery isn't going to cause it too much damage, but you are going to lose electrolyte water. Okay. For a lead acid battery, especially a valve regulated lead acid battery, is that correct? Let me just do this. I've got my whiteboard on here. Let me turn it off for a moment so I can see the columns at the top. Oh, that's not what I want to do. How do I switch off the whiteboard? There we are. Yep, lead acid, overcharge tolerance. It says lead acids have a high overcharge tolerance. I don't think that's necessarily true, especially for a valve regulated a VRLA battery. If you overcharge a VRLA battery, it can go into thermal runaway if left too long. So for a vented cell that has electrolytes similar to the NiCad, yes, it has high overcharge tolerance, without a doubt, because once again, all that happens is that it boils off more water in the process. It can damage the plates if it's over a long period of time, but for wet cells, yes, it has high overcharge tolerance. But for a valve regulated lead acid battery, I would say it is moderate to low. And for NiCads, depending on the technology that's used, it's either low or very low. If you overcharge a lithium ion battery, they're very current sensitive storage devices. If you overcharge them, then we all know what can happen to lithium ion batteries if they are overcharged and there's no protection. They do, unfortunately, tend to go into thermal runaway very quickly and go on fire. Okay. This is the next page of that table. Did I put no, I didn't. I thought I put the website I got this from. It's on the next page, I think. So load current. Basically, we're going to look at these bottom numbers more than anything, okay? What we're saying is for a NiCad, you can get 1 times, so basically you can get the full ampere capacity out of that battery without any issues, okay? For a lead acid battery, they're saying it's 0.2. Now, once again, I've said that I'm not a battery expert. These numbers, what I would say is don't look too much into what these numbers mean, but look at the ratios between each one. So basically we're saying you're going to get 5 times more current out of a NiCad battery of the same ampere hour as a lead acid battery. It doesn't matter what the ampere hour value is. Basically we're saying you can get 5 times more current out of a NiCad than a lead acid. And once again, you can get 5 times more out of a lithium ion than a lead acid. Okay. Operating temperatures, this is discharge only. I think this is kind of an ambiguous value. For a NiCad, it says -40 to 60, and it's saying for a lead acid, -20 to 60 degrees C. You know, I don't like this term discharge only, because in the majority of places where these batteries are going to be installed, they're going to be in float mode operation, and that's the operating temperature that they should be looking at. So for a lead acid battery, they are extremely temperature sensitive. They're very temperature sensitive. They want to be charged at 20 degrees C, which is actually 25 degrees C, which is 77 degrees Fahrenheit. Okay, that is what a lead acid battery wants. NiCads really, although you do have to adjust the float voltage to the temperature, they're very tolerant to cold temperatures or warm temperatures. Very, very tolerant indeed. It's not going to cause any damage to the battery, really, in any shape or form. But for a lead acid battery, and even for a lithium ion battery, you can see here at this discharge, you know, the negative temperatures are much higher, much closer to zero. But once again, it's the temperatures when they are being charged. And once again, these are also very temperature sensitive. The higher the temperature, the more likely they are to go into thermal runaway. And therefore, they have to have some protection systems in place to stop that from happening. Now, once again, I've told you I'm not a battery expert, so I'm relying on this information here. And this is always debated by all of the manufacturers. It could be, once again, a little bit wrong, but it gives you a general idea. And once again, forget what they're basing it on. Let's take the cheapest. Let's say that a lead acid battery has a value of $25. What we're looking at is the ratio. So what they're saying here is for a lithium ion battery of the same size and capacity, you're expected to pay 4 times as much. I don't think it's quite as much as that these days. I think it's now down to 2.5 times as much. You would have to check with your battery manufacturing rep to see what they are. But it's just to give you an idea. NiCads, they're about twice as expensive as a lead acid battery. Okay, so that's what these numbers mean. So lead acids are definitely the cheapest. NiCads 2 times the price. I would say lithium ions are about 2.5 to 4 times the price, and that price is always coming down, except for in the market that we're in just now. Everything is pretty scarce. So if you're looking at things as at a cost per cycle value, then NiCad is by far the best. You're going to, it's 4 cents per cycle compared to a lead acid, where it's actually 10 cents per cycle. But I don't know who looks at it in that respect. And then this bottom one gives you an idea of the ages of the technology. So it says here that valve regulated batteries were invented in 1970. That's the maintenance-free non-fillable batteries. But the actual lead acid battery was invented, I think it's actually before 1870. It was back in 1840. So this technology has been around forever. Okay. NiCad technology has been around for 70 years now, which been in commercial use since 1950. And lithium ion, this first technology in 1991, and the technology that a lot of people are moving to now has been around since really 2000, so 22 years old. So this is still definitely a newer technology, and it's changing all the time. And here's the website where I got all that information. I'll leave that up on the screen for a while, and I'll leave it on the screen as well, because there were, in the table, there were some notations, and that tells you what all the notations are. I'm not going to go through them, but it's just when you look back on YouTube, it will give you an idea, and you can stop it, have a look at it, and go back and see what it applied to. But this chart's really the easiest one to look at. And that is the advantages and disadvantages of each technology. So for NiCad, the advantages are you'll get a high number of charge-discharge cycles, okay? Very good load performance, a long shelf life in any state of charge. Pretty much you can leave a NiCad to go near enough down to 0 volts. I know it sounds strange, and then recharge it, and it will be good to go again. Very, very long shelf life in any state of charge. Simple storage and transportation. Most air freight companies accept NiCads without any special conditions. They perform well at low temperatures, and they are forgiving if they're abused. They are really very good batteries when it comes to being abused. They are the most rugged rechargeable battery out there, and they're relatively economical priced, and available in a wide range of sizes and performance options. The limitations, their energy density. You know, to get the backup power you want, you're going to need a physically big battery, especially compared to lithium-ion systems. There is what's called the memory effect. I don't know how much truth is in the memory effect. NASA did find that there were some memory issues with some NiCad cells, but that was a specific type of NiCad cell. I don't think that's really applicable to the industrial NiCads that are out installed in plants all over the world anymore. They are very environmentally unfriendly. The NiCad cell contains toxic metals, and some countries are limiting the use of the NiCad battery because of that. And it has a relatively high discharge. If you do store them, it needs recharging very quickly after storage, because it does discharge itself quicker than most of the other technologies. Lead acid, the advantages: mature, reliable, and well understood technology. It's what's used in the plants all over the world. When used correctly, the lead acid is durable and provides dependable service. It's got a low self-discharge. You can leave it on a shelf and you only have to recharge it after 6 months if it's stored at 77 degrees. Has very low maintenance requirements. It has no memory issues, and for a valve-regulated lead-acid battery, it has no electrolyte to fill. And they're capable of very high discharge rates. The limitations: they cannot be stored in a discharged condition. If you discharge a lead-acid cell below 1.6 volts, then it pretty much can't be relied upon after that. So you cannot discharge it down to 0 and store it and then recharge it back up again. It also has low energy density. Basically, it has poor weight to energy density limits. So therefore, you need a much bigger physical battery, compared especially to a lithium-ion battery, to get the power that you want. They allow only a limited number of full cycles, so they are well suited for standby applications like UPSs. They are also environmentally unfriendly. The electrolyte obviously contains sulfuric acid, and the lead needs to be recycled. So they're not fantastic for the environment. And there are transportation restrictions on flooded lead acid cells. basically due to spillage. If you have a wet cell battery with electrolyte in it, then it is considered hazardous waste. And thermal runaway can occur with improper charging. They can destroy themselves. They can, a lot of people talk about lithium-ion batteries going on fire. Valve-regulated batteries can also overheat and go on fire. And in truth, some vented cells, if they're left long enough in an overcharged condition, can go into thermal runaway and start melting also. Lithium-ion, the advantages, high energy density. And there's, because the technology is new, there's potential for yet higher capacities for smaller size. So the technology is always getting better. So you get much better energy density for a lithium-ion battery. They also have relatively low self-discharge rates, and they're very low maintenance. In fact, no periodic discharge is needed. There's no memory effect. So at this moment in time, there is no maintenance recommendations for lithium-ion batteries whatsoever, which is why a lot of plants are looking into them now, because obviously the maintenance costs for a lead-acid battery are quite high, because you have to follow the IEEE regulations to maintain them. Especially if you're a NERC plant, you've got to follow NERC as well. But with lithium-ion, you don't have to do any maintenance on it. It's all done by the battery monitoring system inside the lithium-ion itself. There's nothing you can do to that battery for maintenance. The limitations, it requires a protection circuit. Okay, the battery is not safe if provoked, it says. Basically, if the battery starts to go into thermal runaway and looks like it's going to go on fire, the only thing that you can do is disconnect that battery from the charging system. And in truth, that does not prevent it from continuing to go into an unsafe mode. But there's a lot of things that are being done in the new technologies, obviously because of Samsung and everybody else. The batteries going on fire, they're much safer than they used to be, but they still have to have protection circuits to make sure that the batteries don't get into a hazardous fire creating state. They're also subject to aging, even if not in use. So storing the battery in a cool place, you will get, and at a 40% state of charge, reduces the aging effect. So if you're storing them, they can age even in storage at high room temperatures. They give moderate discharge currents. They are subject to transport regulations. Shipment of larger quantities of lithium-ion batteries may be subject to regulatory control. Expensive to manufacture, and they're not fully mature yet. There's still a lot of changes happening in the metal and chemical combinations which affect battery test results. So there's a lot of technology advancements being made. So it's still what we class as not fully mature. So hopefully that gave you a good overview of some of the battery types out there. I think this is the last question. So if you have any questions that you want to ask yourself, just put them in the chat bar. I will try and get to them. So the last question was, is there an easy way to check for sync between the inverter and bypass? Well, obviously the first way is on most of our systems, they're going to have an LED or something telling you that the system is in sync. So that's the first easy way. But if you want to confirm it, then there is an easy way you can do it. So you can see on the screen here, we have two waveforms, a black waveform and a blue waveform. And in truth, I had to move them apart a little bit so you could see the two different waveforms. In a normal system, they are actually going to overlap, and it's very difficult to tell the difference because there is no phase difference between the two. But one is the inverter output and one is a bypass. The blue one's inverter and the black one is bypass. So If you had a completely out of phase system, which you can see in this waveform here, the lowest peak of the bypass compared to the highest peak of the inverter is the full peak-to-peak voltage of a for this example, it's a 120 volt sine wave. So the peak voltage is 170 volts, peak to peak is 340 volts. So you can measure up to 340 volts for a sine wave that is exactly 180 degrees out of phase. Okay, there is going to be 340 volts when it gets to the peak of that. There is that voltage potential between the two. And therefore, if you parallel those two together at that point, there is going to be a huge amount of circulating current, because basically paralleling them together is a short circuit. And a high voltage, very low resistance, creates a lot of current. So that is why it's important to be in sync when you transfer a system to bypass. And even if waveforms are only slightly out of phase, okay, you can see here that the phase difference is only a very small amount in electrical degrees. I don't know exactly what it is in this, but you will see here, remember, a sine wave is, you have to measure differences at any single point in time, and that's what this is doing here. What we're saying here is there is a voltage difference of approximately, what did I say, about 30 volts there? About 30 volts between this point here on the inverter and this point here on the bypass. So basically, if you put your fluke meter, your red cable on the live or the hot of the inverter, and your black cable on the live or hot of the bypass, then you will measure about 30 volts AC. And then also, not only phase displacement, you can see here that these waveforms are actually perfectly in phase. The difference in this one here is at the bottom and the top, there is a voltage difference. The inverter voltage is higher than the bypass voltage. So let's say the inverter voltage is 122 volts, and the bypass voltage, which is dependent on power from your MCC, let's say in this system, is 116 volts. That's a voltage difference of 6 volts AC. So if these waveforms were absolutely perfectly in phase, there is no electrical phase displacement between these two waveforms whatsoever, you are still going to measure a 6 volts difference, roughly, because of the change in voltage between the inverter and the bypass. In truth, you are never going to see an inverter and a bypass voltage perfectly in phase. There's always going to be some slight difference between the two. And I would anticipate that you're going to see, let me go back to this one, on your meter, if you measure anywhere between 5 volts to 25 volts, then as long as these values are constant, then that kind of proves that you're in sync. If these numbers here are cycling, if it's going up and down, then that means you're not in sync, and the phases are just moving independent of each other. So for an okay reading, I would say between 5 and 25 volts, measuring the live or the hot of the inverter compared to the live or the hot of the bypass. And I'll show you on a drawing how you do that. So what we're saying here is our bypass source is coming in here, and it goes into our UPS at this point here. So wire 110 is our bypass supply, and wire 199 is the output from our inverter. Okay, and you can see we've got our waveform here and our waveform here, and you'll see on the next page that they are in phase with each other through these dotted lines, the peaks and the troughs. are completely in phase with each other. Actually, on this slide here, I said you're going to see approximately a difference of 5 to 20 volts on a healthy system that is in sync. Okay. Now, for a system that is out of sync, you can see here that we are at the top of our sine wave here, but we're in the trough. We are at the bottom of the sine wave here because at that moment they are completely out of phase. Then across wire 110 and 199, or you can even do it in the bypass switch if you want, there is going to be a difference of 340 volts at the peaks. Okay. Now, what this slide is there to show you is if you then, what the bypass switch does is it closes this contact here before it then opens this contact. Sorry, not that contact. It closes this one and then it opens this one. So it is making this contact. And if this point here and this point here has a voltage difference of 340 volts, when you close that contact, high circulating current will flow from the bypass supply back into the inverter bridge and will probably, it could cause damage to the inverter bridge, and more than likely it's going to trip the breaker that feeds the bypass supply because it sees the high current. And then obviously you've moved this switch to the bypass position, and if you don't have bypass available, then your load no longer has power. It will be a load drop. Okay, so that's why it is important to make sure the system is in sync, and that's the easy way to do it. Wow, 1 hour exactly. I'm getting better. Now we're open to any questions, and while you think of any questions, I'm going to go through the questions that we've had so far. Is it possible now, or are there any potential plant in the future to be able to interface an AMETEK UPS system with a solar voltaic system as an additional backup energy savings? Well, all photovoltaic systems are DC, so basically there are UPS manufacturers out there who are designing their UPSs to go into the photovoltaic industry, the solar industry. They're very cost sensitive and they're very size sensitive as well. So industrial UPSs aren't particularly used in that field, although they can be. But yes, if you have a solar panel on your house, basically that solar panel is DC. You're going to have some form of storage battery on your system, hopefully, and then that DC then goes into an inverter, and that inverter provides power to your house when there is a power outage. So most all solar voltaic systems kind of need a UPS. They need an inverter. The only difference between an inverter and a UPS is that a UPS has a charger installed as well. And that's, you will have to have some form of logic to not use the power from the charger when the solar cells are on, because you don't want to use grid power that costs money when you have solar power available. So that's the kind of things that the specific manufacturers of solar voltaic UPS systems have to look into, how to try and save as much money as possible, and they use electronic logic systems to do that. I hope that answers your question. Which battery type is recommended to use with AMETEK UPSs? Do I have a preference? I do have a preference. I like wet cell lead acid batteries. They are just tried and tested. Yes, they take up more room. Yes, they don't have as much energy density, but you know what you're getting with them. They're very, very, very reliable. And in truth, valve regulated lead acid batteries are also getting much, much better. And right behind that is NiCad. But the problem with NiCad in the North American market is disposing of NiCad. I may be wrong in what I state here, but there's very few manufacturers of NiCad industrial batteries in the US. Okay, if you go to Alcad or Saft, most of their stuff is made in Sweden or somewhere else. So therefore, those countries have a relatively okay way to recycle NiCad batteries. But because there is really no big manufacturing plants in the US for NiCad batteries, it's very difficult to recycle them. And usually you have to pay to get them recycled. With lead acid batteries, you can actually make a little bit of money when you recycle those. But with NiCad, you have to pay for the recycling, and it's just not a great situation. So if they figured that out, I would suggest that NiCads are just as good as lead acid batteries, if not better, to be perfectly honest. But until they get that sorted out in North America, I would still go with lead acid batteries for a UPS system. We are seeing some people use lithium ion on UPS systems. The technology is still new, and we all have it in the back of our head that lithium ion batteries go on fire. And I don't know how many years it's going to take for them to reassure us that they have got that figured out. I think it's great that some people are looking to use new technology in their systems, and that they break the ground for everybody else. But I'm kind of old school. I would like to see everybody else test them before I install them myself. Okay, what else do we have? Can you put a sync check relay in the circuit to prevent switching into bypass out of sync? Yeah, we do sell remote manual bypass switches that have a sync check relay inside them, and they prevent the switch from being switched if they are out of sync. We can do that. So the answer to that question is yes. Somebody says, someday I would like an understanding of float versus discharge versus equalize conditions, especially float versus equalize. He's going to drop off, so thanks again. We do have in Houston, actually we have a class going on just now. It's 2 days of battery training and 2 days of UPS training, and the battery expert we use is Bob Leslie, and he's extremely well versed in the battery industry. And I just spoke to him yesterday and asked if he would be prepared to present one of the webinars in the future on batteries for us, and he said yes. So what he asked me to do is get as much information from our client base and our webinar viewers as possible as what battery questions you would like answered for when he does his webinar. So he can then create a presentation and give you exactly what you need. So Bill, I'm going to put this question into that pile for him. And hopefully within the next 2 months, you will see an email newsletter go out that will tell you that the battery webinar will be up and coming. So please, anybody, if you have any battery questions, send them in the survey or send them in this chat bar here, and or even email us. Taylor's going to put the details of how to get in contact with us in the chat bar. You can go to our website, which is AMETEK Solidstate Controls, and she's going to give you the email address as well. And you can get in contact with us, and we do read the emails. The webinar emails come to me. I read every single one of them. Okay, we have another question. Thank you, Taylor. That's 2 questions we've had about float and equalize. So I'll quickly touch base and give you a little bit of idea of how it works. So float mode is the mode that all batteries should be in the majority of the time. And basically what it does is it's a voltage that is just above the self-discharge voltage of the the battery chemical that's used itself. So for example, for a lead acid battery, they're supposed to be float charged at 2.25 volts per cell. And I think the self-discharge voltage is about 2.18 volts per cell for a lead acid battery, if I'm correct. And there are some losses in the charging process, some heat and stuff like that. So the battery manufacturers have decided that 2.25 is the perfect voltage at 77 degrees Fahrenheit to keep the charge inside your lead acid batteries maintained at 100% pretty much. Okay. So for lead acid batteries, for vented lead acid batteries, not really for valve regulated lead acid batteries, the equalized voltage should only be done when proper maintenance is being performed on that battery and some of the cells in that battery go out with the tolerance that the manufacturer stipulates. And you would have to go to the battery data sheet to see what that is. But in most cases, it's plus or minus 0.5 volts. So if it goes to, for a lead acid battery, if one of the cells measured above 2.3 volts, or if one of the cells measured below 2.2 volts, then the recommendation is to perform and equalize as per the battery manufacturer's instructions. So therefore, for a lead acid battery, you would press the equalize button on the charger and you would equalize that battery for the time that the manufacturer specifically says. And that's where it gets confusing, because what a lot of people don't understand is, let's say the battery manufacturer says for their battery, you should equalize it for a lead acid battery, it's usually 2.38 volts per cell. And let's say they say 2.38 volts per cell for 72 hours. That doesn't mean you press the equalize button and do an equalize for 72 hours. That would be easy. Unfortunately, the 72 hours starts when the battery, the current going into that battery from the charger, once the equalize button has been pressed, stabilizes for over an hour. In other words, doesn't change for over an hour. So when you press equalize button, the battery will start accepting more current, and then eventually it will start tailing off. And then what you're supposed to do is take a measurement every hour of current going into the battery. And when that current going into the battery doesn't change over a 1 hour period, then that is when your 72 hours start. So that sounds kind of complex. It sounds like a bit of a pain, to be honest. So what most people do is, okay, if the battery manufacturer says equalize for 72 hours, they put about another 24 hours on their timer, knowing pretty much that the current will stabilize within 24 hours, and then start the time. That's not a problem. You know, an extra day of equalize is maybe going to boil off a very small extra portion of the water inside the battery, and that can be topped up. It's not really going to cause the battery any damage. So hopefully that gives you an idea of float and equalize. A lot of people say, oh, I go and equalize my batteries every 6 months. There's absolutely no need to do that whatsoever. You only equalize the battery when some of the cells go out of tolerance and equalize as per the battery manufacturer's recommendations is required. So hopefully that explained float and equalize. Taylor's put in the chat bar that the recording of this presentation will be uploaded to our YouTube channel, and there is the link to our YouTube channel. By tomorrow, it should be uploaded, because they do have to download it to MP and then convert it to MP4 and then upload it back to the YouTube channel. And also you will receive a follow-up email tomorrow with a direct link to that recording and a brief survey. So please do fill in the survey. We do rely on those surveys to figure out what we're going to discuss at our next webinar. So if you get the survey, please take the time to answer. I think it's question 5 or question 6. What would you like to see at the next survey? And I do read every single one of them. Okay, well, we don't seem to have any more questions. So thank you very much for spending just over an hour with me on your Wednesday morning, afternoon, or evening, wherever it is where you are. I do really appreciate you taking time out of your day and listening to me waffle on for the last 60 minutes. It is appreciated. Hopefully you gained some information that you didn't know before we started today. That is the aim. And hopefully you enjoy the rest of your week, and we will speak to you again next month. Look out for the email that tells you what we're going to be talking about next month, and I look forward to speaking to you again. Take care until then, and thanks for watching the AMETEK Solid State Controls webinar for the month of March 2022. Take care.